Thank you for your introduction. Today, I'd like to introduce the protein language model for exploring viral fitness landscape. It is known that recurrent viral epidemic surge are caused by the emergence of new variants. This plot shows the epidemic dynamics of SARS-CoV-2 in Japan. As you can see, the emergence of Alpha, Delta, Omicron BA1, BA2, and BA5 cause new epidemic surge. Such kind of epidemic pattern suggests that variant with higher fitness becomes the next variant and cause the next epidemic surge. Therefore, if we can identify the next variant at earlier epidemic phase, we can forecast the initiation of next epidemic surge. Furthermore, if we can characterize the property of next variant, such as pathogenicity or drug resistance using experiment, we can evaluate the risk of epidemic surge caused by the next variant in advance. Therefore, we have developed the methods to identify the next variant with higher fitness. Viral fitness can be estimated as effective reproduction number, RE. This reproduction number means the average number of secondary infected individuals in a certain condition. For example, this variant A reproduces one secondary infected individual, therefore reproduction number of this variant A is 1. On the other hand, this variant B reproduces two secondary infected individuals in the same condition. In this case, we can say that variant B reproduction number of variant B is twice higher than variant A. Furthermore, if we monitor the co-circulation of variant A and variant B using viral genome surveillance data, we can observe gradual replacement of the epidemic variant from variant A to variant B like this. Furthermore, by fitting logistic regression model to this kind of data, we can estimate the relative fitness between variants only based on the viral genome surveillance data. This is typical method to estimate the viral fitness from the viral genome surveillance data. However, there are limitations in this conventional method. The conventional method needs the accumulation of many viral sequences. Therefore, to estimate the fitness of an emerging variant, we need to wait the accumulation of the sequence of this variant. Therefore, we need methods that can identify the variant with higher fitness immediately after their emergence. In this study, we have established a fitness prediction model, COVFIT. COVFIT can predict the reproduction number of various variants only based on the spike protein sequences. Using COVFIT, we can understand the genetic basis of virus evolution or how viruses enhance their fitness. Furthermore, by scanning newly registered sequence in the database using COVFIT, we can identify an emerging variant with higher fitness immediately after their emergence. Furthermore, viruses tend to evolve to increase their fitness. Therefore, using COVFIT, we can predict the direction of virus evolution. We established COVFIT using protein language model. As you know, protein language model is a kind of language model pre-trained on the large collection of protein sequences. And this protein language model learns the general rules of protein and can be fine-tuned for specific tasks such as prediction of viral fitness. In this study, we trained protein language model ESM2 using two distinct information. One is the SARS-CoV-2 variant fitness data. This data includes a reproduction number of various variants estimated from genome surveillance data. And second information is effect of each mutation on viral immune escape. We utilize the result of deep mutation scanning experiment. In this experiment, all possible single amino acid mutations are inserted into the spike protein, and then the effect of each mutation on immune escapability from neutralizing antibody are measured systematically. We trained ESM2 model using these two information with a multitask learning scheme. Owing this multitask learning scheme, we can transfer functional knowledge of mutation for fitness prediction. Next, we evaluated the prediction performance for future variant of COVID. For this purpose, we splitted variant fitness data according to their emergence date into past and future variants. Subsequently, we trained COVID only using the past variant information and then evaluate the prediction performance for future variants. This is a prediction result. X-axis indicates a fitness value, and Y-axis indicates a predicted fitness value. And each dot indicates each variant, and variants are colored according to the data splitting scheme, a future variant or past variant. As you can see, we can observe strong positive correlation in the past variant dataset. Furthermore, although the correlation score are a bit lower, but we can still observe the strong positive correlation even in future variants. This left panel shows a plot only for future variant. In this plot, variants are colored according to the minimum amino acid distance from the variant in the past training dataset. As you can see, COVID can predict the fitness value for future variant even for variant with greater than 14 mutation compared to training past variants. Together, this result suggests that COVID can predict the fitness not only for past variant, but also for future unknown variant with a certain degree of accuracy. Next, we established a new method to understand how viruses enhance their fitness by COVID. First, we reconstructed phylogenetic tree of SARS-CoV-2 variant according to spike protein sequences. After that, we reconstructed the ancestral sequences of each internal node in the phylogenetic tree using ancestral sequence reconstruction methods. Next, we predict the fitness value for existing and reconstructed ancestral sequences using COVID. Then, we compare the fitness value between the parental and child nodes, and then we identify the phylogenetic branch where the viral fitness substantially elevated. Finally, we identify the mutation associated with such kind of fitness elevation event. This plot shows the predicted fitness on the phylogenetic tree of Omicron variants, including Omicron BA1, BA2, BA4, 5, and XBB. This is a time-calibrated phylogenetic tree, and color indicates the predicted fitness of each existing or internal ancestral node. As you can see, variant fitness have elevated gradually during Omicron evolution. Then we identify the fitness elevation event using the scheme I described above. In this plot, each pink dot indicates the fitness elevation event. As you can see, we identified greater than 500 statistically significant fitness elevation events during Omicron evolution. And then we extracted mutations that are associated with fitness elevation event. This plot shows the top 20 mutations. Today I'll skip the detail, but we found that these mutations are strongly enriched in the mutation in the receptor binding domain, RBD, that are strongly associated with immune escape from neutralization by monoclonal antibody. Together, we found that immune escape could be the critical mechanism to increase viral fitness. Finally, we predict viral evolution by COVID-based simulations. Specifically, we predicted what potential mutation could increase the fitness latest variant, Omicron JN.1. For this purpose, we computationally inserted all possible single amino acid mutation on the spike protein of the JN.1 variant. And then we infer the fitness gain by each variant by each inserted mutation using COPFIT. And this is a predicted result. Y-axis indicates the fitness gain by each mutation, and dot indicate each mutation result. And mutation are ranked according to this y-axis value. As you can see, COPFIT predicted that Gen.1's fitness would be enhanced by the acquisition of F456, K478, and R346 mutations. But this is a prediction. Therefore, we examined whether Gen.1 subvariant acquiring this specific mutation actually emerge and spread in the world or not. And this is the result. X-axis indicates the data information, and Y-axis indicates the proportion of each Gen.1 subvariant. And each panel indicates a Gen.1 subvariant harboring this specific mutation. As you can see, we found that Gen.1 subvariant harboring this specific mutation actually emerged and then spread rapidly. This result suggests that COPFIT can be used for prediction of virus evolution by a single amino acid mutation. Summary, COPFIT can predict the fitness of unknown future variants with a certain degree of accuracy. COPFIT can identify the fitness evaluation event during virus evolution in high resolution. Furthermore, COPFIT can be used for predicting virus evolution by a single mutation. Together, our study suggests that monitoring high-risk variants can be transformed by COPFIT to more efficient way. Finally, I have one announcement. My supervisor, Dr. Kei Sato, has a keynote today. Please join this keynote presentation today. And I'd like to thank you for all the members of Sato Laboratory, particularly the member of my bioinformatics team. Also, I'd like to thank you my research grant supporting this study. Thank you for your listening.
We have time for questions.
Thank you very much for your great talk. And the sequence data of SARS-CoV-2 has very large bias because almost all sequences are obtained by the virus strain causing a pandemic. But I guess predicting the landscape accurately originally need non-pandemic strains. So how can you remove the biases, such biases?
You mean the bias within SARS-CoV-2 or between viruses, you mean?
Yes.
Which one? You mean the bias within SARS-CoV-2?
Yes. Yes. If you the fitness landscape, so I think you are the landscape you made is made by the only pandemic strains, but predicting the future strains, and I think you need a more general landscape containing pandemic and non-pandemic strains.
Okay, thanks so much. I think if a variant has a higher fitness, in that case, this variant will spread around the world. Therefore, I think in that case, we can capture such kind of variant. In other words, if there is a variant we cannot observe, in that case, these variants have lower fitness. In that case, I think it's not so important to include such kind of unobserved variant because these variants have lower fitness. How do you think about it?
Yeah, thank you.
Thank you.